Hello, Prop Stacks, and welcome to 10-2. This is regression. We've already covered part of this. We're just going to go more in depth, so you will need stat disk. And let's go. You'll also need your data for your length of your right foot and your height. So if you can get that off of our surveys, we'll be ready to go. All right, make sure stat disk is up and you got your notes. Okay, when you're looking at this here, regression, our objective is we're going to use a paired sample data. We're going to create the regression line, and then we're going to predict values off of this regression line. Now, if you remember, we had a paired sample. The regression line was always in the form of y. We wrote this a little different. Instead of the b0 plus b1x, we wrote it in the form y. Whoops. We wrote it in the form y. All right. Hopefully this starts to work. Y equals mx plus b. And remember this here from stat disk. This here was b1, and this was b0. So nothing different than what we've done there. Okay, requirements. We have to remember it has to be a random sample. You have to do a visual examination, make sure it actually looks like a straight line. And outliers are bad. So we have to make sure that we remove the outliers if we have any. And that we're actually just going to do by looking. All right, 2 and 3 are just formal requirements of this, is that they have a normal distribution. 2 and 3 do this for us when we're looking at that. That's what our straight line looks like our visual examination, and our standard deviations when we remove the outliers. We're going to round to 3 significant digits, and we'll use stat disk for most of this. All right, so here's our technology. We're going to use our x variable and our y variable, and we're going to look at the Nobel laureate rate compared to chocolate. All right, now I know that chocolate does not make you have a Nobel Prize, and so do you. But is there a correlation? But we know there's no causation, right? Requirement check. We're going to assume it's a random sample. It probably isn't, so this probably doesn't work well, but we're going to assume so for the moment. We're going to plug in our data. So when you go to your stat disk and you go to your data sets, the Nobel laureate one is on there. And when you plot your scatter plot, you will see it is close to a straight line. All right, there are a lot of outliers here. Not outliers, but they're farther away, so it's not a real good fit, but it is close. So there are no true outliers because nothing is crazy away from it. All right, so now when we type this into stat disk and we go to our regression coefficients, so analysis, correlation, and regression, and we do our 2 data points. So we're going to do x is going to be your foot and y is going to be your height. Type that in and we find our b sub 0. All right, so we got the negative 3.1 and the 2.4. I prefer this written as y equals 2.47x minus 3.16, but you can do it the other way. It is not wrong. We're going to be learning what all of these values mean and these values to help us decide how well this goes. Okay, the regression equation is just an estimate, all right, of the true regression equation for the population of paired data, because we're using a sample. So it's just an estimate. It's usually fairly close. It could be slightly different depending on your different sample data. All right, so let's use our stat disk. Okay, we've gone in, we've looked at our data. Okay, the regression line fits the points well, but the points are not very close to the line. That means there is a lot of variation, which is not necessarily good, or a lot that is not represented by the line itself. Okay, let's look at what a good model is and a bad model. A bad model, it does not appear to be useful. So the regression equation does not appear to be useful. It is very far away from a line, okay? We cannot use it. A good model, the regression predicts only the graph, the regression, and scatter plot conform. That means it does look like a line at best fit. Okay, the correlation, all right, is the R value, indicates that the line correlation, like how good does the line represent the variables that we have. The scope, and we're going to use that there to predict different values. So not far off of our value data because that doesn't work well, but close to our data values, like a little bit above or below. These are your strategies. You look to see if it's a good model. If it's yes, you create your equation. If it's not, you cannot do this, and we will use the mean instead to predict what is going on. All right, chocolate versus Nobel Prizes. All right, so we decided it is a good model. Kind of a little loose fit there because we don't think it's really a random sample, but we're going to say it is. We're going to say the regression line fits the points well, and there is a linear correlation. So after we created our line, which was from StatDisk, this is what we got. I want to know what it is if we have 10 things of chocolate that we eat. So how many Nobel Prizes should I have? And if I plug in 10 to my equation, I should get 21 Nobel Prizes. Pretty good, right? So for every 10 million people, I should have 21 of them that can create or win a Nobel Prize. Okay, I would like you to do the same thing. So pause and use our data that we have from our feet and our height. So pause and do this. Okay, I hope you did well, and I hope you remember to check your requirements. All right, is it a simple random sample? And we're going to say yes. Did you remove your outliers? If you did not, go back and do so and redo this problem. And then check your visual to make sure we have a line. Which after you remove your outliers, it doesn't look too bad. Things that we do not know or we haven't talked about yet. Your null hypothesis for this is actually no correlation. And then your alternative hypothesis is there is a correlation. So when we get the p-value of 0.00 is less than 0.05, that means we reject the null. Since we're rejecting the null, we are saying there is a correlation and we can use this fit. Now once you've figured this out, we go and we create our equation, and you should have got, we probably have different data sets, so it should be close to mine. 3.1399 for x, your slope, plus 37.36. I wanted to know how tall a person should be if they have 13-inch foot. So I plugged in 13 for x, and I got 8 inches tall. Yours should be close, probably not exact. Make sure you check your requirements. This is very important. Must be done. All right? And remember, the null is always no correlation. Okay, marginal change. So when we're talking about this, your marginal change, right here, is the amount that it changes when the other variable changes. So what is it changing by? Exactly 1 unit. This is literally our slope. That's what marginal change is. So marginal change is the slope. So the marginal change and the slope are the same thing. So that's what we use to figure out what's going on here. So when we go down here in our equation, our marginal change for chocolate and Nobel is 2.49, or 2.49 over 1 unit. All right, so I'm going to increase 2.49 times for every 1 unit of capita. So the rate will be 2.49 per every 10 million people. So every 10 million people I add, I should have 2.5 more Nobel Prize winners, is what that is saying. What is the marginal change for your feet data, and what does it mean? So pause and write that down. Okay, when you looked at it, so my slope was 3.134. Technically, we put that over 1. This means for every inch that's an inch, sorry, that your foot increases in size, your height increases by 3.134 inches. Kind of weird, huh? Remember your outliers? All right, right now we don't have a good way to find outliers other than you could look at each data set, but you've got to remember the outliers lie far away from the other data points. So if they are weird, you have to take them out. In statistics, we call those influential points. So if I remove the point, if it changes my equation for my line, it's an influential point and must leave. Some of them are very obvious. So like when we were looking at our height, you would take out all the ones below that where the height was not in inches, basically. So we had like our double digits, our single digits are definitely influential points. We took those out and changed our equation drastically. So those needed to leave. Here in our chocolate consumption, if I added 50, so I added this point, see how drastically my line changed and how far away from the other data points it is. So this one is considered an influential point or an outlier. And that's how we know it has to be removed. So it's more on a visual inspection right now, and then checking what happens to the equation once we remove a point. Okay, a residual is how far away our data is from the line. So when we go here and we're going to look at our residuals and what we observe. So these are the points. I graphed these points right here in StatDisk. Now, when you look at the residuals, here is this point, right? The point, how far it is from the line, is the residual. This point here is 7 away from the line. That's its residual. This guy is negative 13 because it's below. Negative 5 because it's below. So the residuals tell you how far away they are. So the larger your residual, the worse it is. So let's go here. This is my equation of my line, and I want to consider 8, 4. That's my sample point. So when I put my point is 8, I have 4. This is actual. All right, when I plug in 8 into my equation, I actually get 9. So the residuals, how far apart is the actual from what I should get? So 4 minus 9 is negative 5. It's 5 below where I should be. All right, you do the same thing. Pick a point and calculate your residual for your feet. So I picked, on mine, I had an 869 was my point. I plugged it in. So I picked 3.134 times 8 plus our 37.36, and that equaled 62.4. So how far away am I? So I'm going to take the 69 minus the 62.4, and I'm 6.6 away. That's my residual. Okay, another name, this is just notation, a least squared line is the same as a line of best fit, so sometimes that's what it's called, a least squares line. Okay, residual plots. When you go onto StatDisk, there is a residual plot. So when you click on and you did your scatter plot up here, right? Click on the next one beside it that says residual plot. And when you look at this to tell if it's good or not, there can be no obvious pattern. So my dots can't go like that. All right, there can't be a pattern. Okay, if there's a pattern, it's bad. The other thing it cannot do is it cannot look like it's getting like this. My dots can't go like that. All right, this one, because of this guy, doesn't. But if that wasn't there, then we would say, hey, this is bad too. The other thing it cannot do is go the other direction. So your dots can't form a funnel, in other words, in either way. So if any of those, if there's a pattern or if there's a funnel either direction, we cannot use this. It is not good. It's called your residual plot. Another way of visually looking at your graph. Oh, here they are down here. So this one here has no pattern. This one here has your pattern. If you look here, see a pattern kind of forming. This one here gets larger. So it has a funnel. So this is bad, bad, or not good, not good. And this guy's good. So you kind of see what they look like. So if they're not good, we cannot use our line of regression. Okay, look at your residual plot for your height. And if you look on mine, you should first step, there was no obvious pattern. And second, there was no funnel. Since both of those are met, this would be a good model. We can use our line of regression. All right, good luck on your homework. Make sure you post questions, and we'll talk to you later. Bye.